Okay, we're gonna do another single replacement reaction. However, we're gonna go through the steps by just knowing a couple of reactants, how you could try to predict the products and by predicting what type of reaction it is. Okay, so what is the equation for reacting potassium hydroxide and tin? It's regular old tin. Okay, so we need to first write each reactant and make sure those formulas are balanced, and then we need to predict products, and then we are going to make sure that we identify the products well enough and balance the equation, and I'll go through the steps a little bit. So in reality, potassium hydroxide and tin do some funky stuff, but don't worry, in regular chemistry, in my class, we're gonna assume that it just does kind of, it's standard types of chemical reactions that we study, so nothing weird. But I'll tell you a little bit about what actually happens. For now, all you have to say is potassium hydroxide reacts with tin. So you're going to write the first reactant, potassium, and hydroxide is an IDE ending. Also, it's a polyatomic anion, so you know that this is an ionic compound. Also, potassium is a metal and generally will be a ionic compound with anything else. So potassium likes to be +1, it's an alkaline metal. Hydroxide is a polyatomic anion, and altogether it likes to be -1. It is -1. Just, yeah, assume it is. So then you're gonna put a little plus sign and put the other reactant, which is tin. Just write tin once. It's just a neutral metal that can react. All right, so what we're gonna do is look at the reactants and say, okay, what could they be? They're going to be a cation or an anion. Metals always become cations, so tin is definitely going to become positively charged cation. I happen to know tin mostly in this situation likes to be +4. That you may have had to get extra information to be able to solve this problem, because it's a transitioning element, and so it could be one of a couple things. So it will eventually become +4. So just think of it as, yeah, it's going to be positive. We can't put the potassium with the tin because they're both positive and they're going to repel each other. So we put the cation with the other anion. If something's going to happen, that's what's going to happen. You're going to have a partner switch. And as you can see, we draw a single arc to show one new partner going with the other partner. And it's a little single rainbow. You can think of it as a single rainbow. If we had a double displacement, we would have another partner for that potassium to go with an anion, and then it would have 2 lines, and it would be a double rainbow. So double rainbow, or sorry, we're doing single rainbow. Single rainbow, and the initials also are single replacement, so, or single displacement, you can call it that. But single replacement is also kind of clever, because then if it's got 2 rainbows, then it's a double rainbow, that's DR, and then it would be a double replacement reaction. But since we have only one partner switch with, it's a single replacement, okay? So what you'll do now that you have your reactants properly placed and they don't actually have a charge, really, or we don't write a charge on them, we're going to write what the new partners would be. Cation first. Tin is going to become a +4. I always say 4+ instead of +4, because sometimes students get confused that we're adding 4. No, it just has a +4 charge, so I read it that way. And then you're going to put the anion with it. You just write each once for starters and write their charge. All right, remember, you need to cross the charges. That's one way to think about it. The 4 goes here, the 1 goes there. We know we never put a 1 when there's a 1. We just leave it blank. Or you can think of it more specifically that we have a +4 charge here, and it's going to need a total of -4 charge. So we put parentheses around there to show that we're going to have multiple sets of hydroxide to balance the charges of the tin. So you're going to put a 4 here. That's subscript just means I need a ratio of 4 hydroxides in this compound for every 1 tin. Okay, you can erase the charges. And then the only thing that's left is the potassium. It doesn't have a partner. So in this situation, you could say, oh, it's going to get kicked off by itself as a metal, which is highly improbable, but I mean, could happen if you had a good catalyst. That's okay. That's the way we're going to treat it. If you want to, you can put like the fact that this could be a solid metal. I don't know. Then what we need to do is balance the equation. So what you'll do is look and see what's weird, okay? I've got one potassium and one potassium on each side, all right? One tin and one tin. It's the oxygen and hydrogen that are the problem children. So what you can do is, I like to kind of do the rainbow method. That's one method of balancing, just to show you, even though this is pretty simple. Hydrogen, because of the 4 in the corner, is going to have 4. That means 4 hydrogen atoms are being given off. And if you leap here, maybe we can call this leapfrog or rainbow method. If you want to leapfrog or make a rainbow, we know that hydrogen over here only has 1. We need to make it 4. Let's make it 4. Let's put a 4 out front as a coefficient. And that means I have 4 sets of potassium hydroxide, which means I'll have 4 hydrogens, 4 oxygens, and 4 potassium. Before we deal with the others, let's just deal with oxygen actually next, okay? Oxygen, so that's now 4. Leapfrog back to oxygen. Oh, it's already 4. Perfect. Good job. Nothing else changed except for the potassium. So we do need to look at the potassium and say, oh, how much do we have here now? We have 4. So let's leapfrog over here where we only have 1. We can easily fix this by putting a coefficient of 4 down. I guess I could have written it in regular pencil, but you know, why do that if you're holding a colored pencil? The last thing I want you to do is to make sure that you check the balancing. Okay? Well, one of the last things. So you write each atom once in the middle. Here's one technique of doing that. All right, and then you just sort of count them, and the left side goes on the left and right side goes on the right. So you have, oh, let's color code this, because why not? 4 potassiums on the left and 4 potassiums on the right. You have 4 oxygens on the left and just 4 oxygens on the right. Good job. And then for hydrogen, you have 4 on the left, because remember you have that multiplier out front. This says 4, and then you have 4 on the right. And then for tin, it never changed. It's just 1 and 1, but that's perfectly reasonable. And you can write like that, and you know you balanced it. So another thing you might be asked is to predict the products or to write the products. So now you have to name this ionic compound. Remember, you name the cation and the anion. I think it might be stannic or stannite. Actually, I think in real life it becomes stannite. But we just go tin and then the charge, which we decided was going to be +4. So you put the Roman numeral for the positive. That represents the positive charge. That's on that tin. Of course, it gets neutralized by the hydroxide. And then you write hydroxide. I don't know why I capitalize these. It's fun, I guess. You don't need to. So one of the products in this case we're going to say is tin hydroxide and potassium. Just a little old potassium. Normally, potassium really doesn't like to be by itself, actually. It's quite reactive by itself. In real life, this reaction actually happens in water. So this would be perfect. This would be full points for me, and you're great. You're a rock star. But just for funsies, in reality, water actually gets involved in this situation. And as you can see, the ratio of hydrogens would be higher. Potassium doesn't like to be by itself, so it actually joins with the tin hydroxide and becomes like some sort of weird stannite. Tetrahydroxostannate, actually, with a 2 Roman numeral. And then hydrogen gas gets released because you'll have extra hydrogen. And then, of course, the balancing will be completely different. But we don't worry about that. All right. So, yeah, thank you for coming along with me. And, yeah, I have a Band-Aid because, yeah, I have problems. Nervously pick myself. It's gross, I know. Also, as you can see, I tried to paint my nails earlier because I thought it would make my hands look pretty. But then we went and did some tiling, and I just can't leave it. I mean, yeah. So I'm making a new style. It's the nail polish that's, half picked, and that pretty sure is going to catch on to as a major fashion trend. Okay? So hopefully, if you have questions, please ask me, and I will be glad to answer them. I hope you're having a great day, and take care. We'll see you soon.